Hello everyone, myself Vinay Kumaram. I'm pursuing PhD in physics. So in this particular YouTube channel, I'll be teaching physics, chemistry and mathematics starting from 8th standard till 12th standard. So if you want to learn physics, chemistry and mathematics, then please do subscribe to my channel. So in my previous video, I was explaining about natural numbers, whole numbers, rational numbers which can be denoted as Q, and also about integers. And I also solved the exercise 1.1 questions. So now in this particular video, we will try to understand what do you mean by irrational numbers. So now we will try to look upon what do you mean by irrational numbers. So here in the number line, so in my previous video also I have written this particular number line. So in this number line you have 0, 1, 2, 3 and it goes on like this. And also on the left hand side of 0 you have the negative numbers like this. So here in this number line we have natural numbers, we have whole number. If you include 0 you will get whole number, and if you include the entire set of numbers, the full numbers on this number line, you get integers. So now you have to consider the numbers which are there in between 0 and 1, in between 1 and 2, in between 2 and 3. And if you are expressing that in the form of p by q, where p and q belongs to integers, and if q is not equal to 0, then these can be known as rational numbers. So for example, if you consider 1 by 2, so 1 by 2 is a rational number because 1 is an integer, 2 is an integer. So 1 by 2 is equal to 0.5. 0.5 lies in between 0 and 1. Somewhere here 0.5 lies. So that means in this number line, rational numbers are also there, natural numbers are also there, whole numbers are also there, integers are also there. Now, apart from this, are there any other numbers in this particular number line? Yes, there are other numbers also in this particular number line, and those numbers are known as irrational numbers. Then how to identify these kind of irrational numbers? So always remember, whenever you take a particular value, a particular rational number, and if you divide it, you should either get recurring numbers in the quotient or you should get a finite number in the quotient. Then those numbers are known as rational numbers. So for example, if I take 1 by 5 as an example, and if I go on dividing this 1 by 5, so let's divide 1 by 5. So I'll take 5 over here and I'll take 1 here. So 5, if you take 0 point, so that means if you are considering point, then I can put 1 0 over here. So 5 2s are 10. So you are getting 0 in the remainder place. So whenever there is a termination happening when you are dividing a certain number, then you don't have any kind of recurring numbers. You have a finite number in this particular quotient. So now if I take another example, for example, if I consider 7 by 8, so now we have to divide 7 by 8. So 8 I can write here, 7 I can write here. You can put 0 point. So when you take point, then you can put 0 over here. So 8 into 8 will give you 64. So 8 8s are 64. So when you subtract 64 with 70, you are getting remainder as 6. Again, because decimal point we have taken, you can take 0 here. So 8 7s are 56. So again you are getting 4 over here. You can take 40. 8 5s are 40. So here also you can see you are reaching 0. That means the quotient is having a finite value. Now if you consider another example, for example, if you are considering 1 by 7, so if you are doing 1 by 7, here you can take 7, here you can take 1. So if you take point, then you can put 0 over here. So 10 will be there. 7 1s are 7. So you will get 3 in the denominator, in the remainder place. So again you can take 0. So 7 4s are 28. So 7 4s are 28. So you are getting 2 in the remainder place. So you can take 0 here. So 20 is there. So 7 2s are 14. So you'll get 6 in the remainder. So again you can take 60. So here I have taken 7 2s are 14. So now I can take 7 8s are 56. 4 will be there in the remainder place. So again you are getting 4. So 0 you can take 40. You can take 7 5s are 35. So when you take 7 5s are 35, the remainder will be 5. So you got remainder as 5. Again you can take 50. So here you can see 7 7s are 49. So that means again you got 49. So 50 minus 49 is 1. So you can see here also 1 was there. After taking decimal point, we put 0 beside 1 and we got 10. So that means again you are getting remainder as 1. Again if you take 10, again you have to take 7. So which will be 30. So that means again here it will be 7 ones are 7. So that means here again this will go like this: 1 4 2 8 5 7. So that means if you are considering 1 by 7, so the answer for this 1 by 7 will be here I'll write this in the new slide. So 1 by 7 we are getting it as 0.14287, and again this 1428857 will be repeated, and again this 1428857 will be repeated, and this goes on like this. So that means you are getting a recurring numbers. So that means here the same set of numbers are recurring. So these kind of numbers if you are getting, then that is also considered as rational numbers. So that means whenever you divide a particular integer, so for example whenever you consider 1 by 7 or whenever you consider 1 by 5, so all these numbers are known as rational numbers, because the answer when you divide 1 with 7 or when you divide 1 with 5, you are either getting a recurring numbers. So either you are getting recurring numbers in the quotient, or you are getting finite number in the quotient. Whereas in irrational numbers, for example if you are considering an irrational number, there is no recurring set of numbers or there is no finite value. For example, if you are considering root 2 is equal to 1.414213563. It goes on like this. There is no recurring number after decimal point, and also there is no recurring number or there is no finite numbers after decimal point. So here you can see after this particular decimal point, either you should have a recurring number or you should have a finite number. So either recurring number should be there. So here in this case there is no recurring number, or there should be a finite numbers after decimal point, which is also not there. So always remember, after decimal point there should be a recurring set of numbers or there should be a finite numbers. So here there is no finite numbers, it is going on like this infinitely, and also there is no recurring set of numbers. So these kind of numbers, so that is root 2, can be known as irrational numbers. So for example, if you consider pi is also an irrational number, because if you expand pi, so pi has value 3.141592653, and it goes on like this. So there is no recurring happening in this particular numbers after decimal point, and also there is no finite numbers after decimal point. So there is no finite numbers after decimal points because it is just going on like that infinitely, and also there is no recurring set of numbers after decimal point. So that's why pi is also an irrational number. In general, we indicate pi as 22 by 7, which is wrong, because approximately pi is equal to 22 by 7. So always remember, approximately pi is equal to 22 by 7. Pi is not exactly equal to 22 by 7, because if you consider 22 by 7, then it becomes a rational number. Here pi is not a rational number, it is irrational number. So that's why approximately we are considering pi as, so approximately we are considering pi as 22 by 7, but it is not the exact number. So always remember, pi is not equal to 22 by 7. Pi is approximately equal to 22 by 7. So that's why pi is an irrational number. So always remember, for any irrational number to be known as irrational number, the numbers which are there after decimal point, here if you are considering pi, so the numbers after decimal point should be infinite, and also it should not recur. So that means whatever numbers which are coming after decimal point should not repeat, and also it should be infinitely long. So that means it should be going on like this. So that kind of numbers can be known as irrational numbers. So that's why pi is known as irrational number, and these kind of numbers also exist on the number line. So in the start of this chapter, I have given a number line. You have rational numbers, you have integers, you have whole numbers, you have natural numbers. Along with this, you have irrational numbers also. On this number line, you have irrational numbers also. So always remember, on a number line, in this particular number systems, you have whole numbers, you have natural numbers, you have integers, you have rational numbers. Along with that, you have irrational numbers as well. So I'll write this as IRRN. So you have irrational numbers also. So if you include whole numbers, natural numbers, integers, rational numbers, irrational numbers, all these numbers if you are including in a number system, then this kind of number system can be known as real numbers. Why? Because in real numbers, all these whole numbers, natural numbers, integers, rational numbers, irrational numbers, everything will be there. So in the set of natural numbers, it starts from 1, and only the positive values on the number line, and the full numbers, that is 1, 2, 3, 4, 5, 6, it goes up to infinity. So all these numbers can be known as natural numbers. If you put 0 in this set, then that particular set will be known as whole numbers. If you add all the integer, all the negative part of that particular natural numbers, then that particular set can be known as integers. And if you are expressing any number in the form of p by q, that is where p and q are integers and q is not equal to 0, then such numbers can be known as rational numbers. So if you are taking square root of 2, if you are taking square root of 3, the value which you are getting here 1.4, and it goes on like this, here 1.7, and it goes on like this. That means there are infinitely many numbers after decimal point, and those numbers are not repeating. There is no recurring pattern. So such kind of numbers are known as irrational numbers. So those numbers are also included in this real numbers set. So you have a number line like this, 0, 1, 2, 3, and it goes on like this. So now you have to calculate, you have to locate root 2 on this particular number line. How to locate this particular root 2 on this number line? In order to do that, you can consider a particular right angle triangle like this, where 1 unit is the height of this triangle and 1 unit is the base of this particular triangle. Then what will be this particular hypotenuse value? So according to Pythagoras theorem, you have, for example, if I name this as A, B and C, so always remember AB square plus BC square is equal to CA square. So what is AB? AB is 1 unit, so that is 1 square, plus BC is also 1 unit, that is 1 square, which is equal to CA square. So 1 square plus 1 square is 2 is equal to CA square. So that means here CA is equal to square root of 2. We are only considering the positive value of CA because we are considering the length of this particular triangle. So always remember, we are considering the length of the hypotenuse of this particular triangle. So only length of a particular figure if you are taking, then always that will be in positive value. So that's why I am only considering plus root 2 for CA. So now you got what is the value for CA, that is root 2. So the same, this particular triangle what I have written, you can place on the number line. So like this you can place. So here the base is equal to 1. So the triangle starts from here and 1 unit will be there like this, and you can join this line. So here I have placed this particular triangle on this number line, where exactly from 0 to 1 is the base of this triangle, because base of the triangle is equal to 1 unit, and height of this particular triangle is also 1 unit, and this value is root 2. So this is 1, this is 1, and this value is root 2. Now this particular line what you have got is root 2. The same line you can just drop onto this particular number line like this. So you can take a compass, you can place one end of that particular compass here, and you can just draw a particular circle like this, and partial circle like this. So this particular value, so this point I can name as D. So from this 0, that is from the position C to D, this particular length can be known as root 2 value. So that means root 2 lies on this particular D position. So this particular D position root 2 lies. Similarly, if you want to calculate root 3, if you want to locate root 3 on this particular number line, then you can consider a particular number line. So before doing that, if we have a right angle triangle like this, so for example, if we have a right angle triangle, and here if the value of this particular hypotenuse should be root 3, then what will be the values for this? Because here if you are considering this as I'll name something different for this, so x, y, z, if you are considering x, y, z, here xy square plus yz square is equal to zx square. You can consider a number line like this, 0, 1, 2, 3, a triangle which has 1 unit as its base and 1 unit as its height. So what will be this value? This value will be root 2. Now you can consider this as one of the length of a particular right angle triangle, and you can write a perpendicular line to this particular line. So this particular hypotenuse, you can draw a perpendicular line, and let's say this, and also remember this value of this particular line should also be 1 unit. For example, if this is triangle A, B and C, then you will write one more point here. Let's say this is D. So from A to D, the value is 1 unit. From this particular position, you can draw till this 0th position, that is at C. So now you have this root 2 as one length and 1 unit as one length of this particular triangle. So root 2 and 1 is there. So this value becomes root 3. And from this position, you can try to write a particular circle using compass, and wherever this particular circle meets on this number line here on the positive side, so that will be the value for root 3. So this particular position can be known as root 3. Like this you can locate root 5, you can locate root 6, like this you can go on locating on the number line. So now we will try to understand exercises which are there. So first we will try to look into the questions which are there in exercise 1.2. So coming to the first question in this particular exercise 1.2, here you have true or false statements, and you have to justify why it is true or why it is false. So in this first question, coming to the first statement in this first question, here every irrational number is a real number. So here they have given every irrational numbers. So every irrational numbers is a real number. So is it true? Yes, it is true, because real numbers, so answer for this first statement is true, because all real numbers, so real numbers is always denoted as capital R, and rational numbers are always denoted as Q. So always remember, rational numbers are denoted as capital Q and real numbers are denoted by as capital R. So always remember, real numbers include natural numbers, whole numbers, and this also real numbers includes integers, and this real numbers also include rational numbers, and this particular real numbers also include irrational numbers. So that means every irrational number can be a real number because real number contains irrational numbers as well. So answer for this first question is, first statement is true. In the same first question, if you come to the second statement, here every point on number line is of the form root m, where m is a natural number. So here in second question, what they mean is that if you have a number line like this 0, 1, 2, 3, it goes on like this, you have negative numbers also on this particular number line, that is -1, -2, -3, and it goes on like this. So here, can you express every number as the square root of a natural number? It is not possible, because whenever you take square root of a particular natural number, here m is a natural number. So whenever you take square root of a particular natural number, you cannot get the negative values at all, because natural numbers is always the positive values. So whenever you take square root of a positive value, you will get positive value only. That means you don't get the negative numbers. So how to express negative numbers as the natural numbers? So for example, if you want to express 2 on the number line, you can straight away take square root of 4. So 4 is a natural number. So square root of 4 is 2. So 2 is there on number line. But now -2 is also there on number line. How will you take square root of any natural number to get this particular -2? You can't get this particular -2 by taking square root on any particular natural number. So that's why this particular, so by taking square root of natural number, you cannot get -2. You cannot get -2, or you cannot get -3, you cannot get -1. So that's why the answer for this second statement is false, because no negative numbers can be obtained by taking square root of a natural number. So you can justify the answer for this second question by saying no negative numbers. So no negative numbers on number line is obtained by taking square root of a natural number. So if you take square root of a particular natural number, you cannot get any negative numbers which are there on number line. So you cannot express negative numbers by taking square root of natural numbers. So that means negative numbers, so negative numbers cannot be expressed as the square root of natural number, as the square root of any natural number. Now coming to the third statement in this exercise, in this first question, here they have asked every real number is an irrational number. So every real number, so I'll just write capital R, is a irrational number. So here this is also false, because for example, even 2 by 3 is a real number, which is not a irrational number, and also 2 is a real number, 3 is also a real number, so 3 is also a real number, 4 is also a real number. So that means these 2, 3, 4 are not irrational numbers, but they are real numbers, because real numbers contains natural numbers, whole numbers, integers, rational numbers, irrational numbers. So that means here every real numbers is not a irrational number. But every irrational number is a real number, but every real number is not an irrational number, because in real number set, all other natural whole numbers, natural numbers, integers are all included in real numbers. So that's why every real number is not an irrational number. So answer for this third statement is false. So coming to the second question, here they are asking, are the square root of all positive integers are irrational? So that is not true. Here the answer for this second question is also false, because there is square root of certain positive numbers. For example, if you consider square root of 4, then square root of 4 is 2, where 2 is not a irrational number, it is a rational number, because 2 can be expressed as 2 by 1, that is 2 can be expressed as p by q form, where this square root of 4 is equal to 2. So that means here all natural numbers square root cannot be irrational number. So this is all there in this particular video. So the examples which are there here, that is the next examples which are there after exercise 1.2 and exercise 1.3, I'll be discussing in the next video, and also remaining concepts which are there in this particular chapter I'll be teaching in the subsequent videos. So like this, if you want to learn more physics, chemistry and mathematics starting from 8th standard till 12th standard, then you have to subscribe to my channel. Please do subscribe to my channel and stay tuned with my channel. Thank you.